to the next talk, I just wanted to highlight that there's a discussion, 10 minutes discussion after this. So this is the format of XE. So after the last talk, I'll ask all the speakers to come to the front, and everyone who has a question can come to the front as well, so we can actually utilize this discussion time. So the next talk is going to be Stateful REST API Fuzzing, and it's being presented by Douglas Douglas.
Hello everybody, thanks for coming to my talk. So I'm going to talk about RESTler, which is a stateful REST API fuzzer I built in collaboration with Patrice Godefroy and Marina Polisuk from Microsoft Research. So in the context of this work, we were interested in cloud services that are running, like those that are running in AWS and Microsoft Azure. The cloud services are forming a rapidly evolving ecosystem, and basically REST APIs are the traditional way to access those services. And then the question is, how do we test those services that hide behind REST APIs? And today we are going to discuss a new approach, stateful REST API fuzzing, and we will compare it and contrast it with past approaches that have been tried so far. So what have been people doing to test REST APIs? The first way is grammar-based fuzzing. Basically, you have an API, you know the specification, and you write a grammar which describes how to fuzz its request type. The challenge with this approach is that it requires a lot of manual effort, and basically for each new service, you need a new grammar. Another approach that has been tried is by using HTTP fuzzers, because since REST APIs are sitting on top of the HTTP protocol, you can basically use HTTP fuzzers, record some traffic, fuzz it, and then replay the traffic, hoping to find some bugs. The main drawback of this approach is that it first requires live traffic, and then the second drawback is that it's not stateful in the sense that the mutations are happening at the individual request level. The third approach that people have been following is by building custom specific tools for their APIs, and this is a very labor-intensive approach and difficult to maintain. Our solution is a little bit different. It's RESTler, a stateful REST API fuzzer, and I need to define here what do we mean by stateful. So by stateful, we basically mean that the tests produced by RESTler are sequences of requests instead of a single request, and by generating sequences of requests, you are basically able to exercise latent states of the service and hopefully find deeper bugs. How do we achieve this? We achieve this by two key techniques. First, we do a static analysis on the specification of the REST API, and we infer dependencies between different request types. By dependencies, I mean, for example, here that if you have a request B, which is consuming a resource ID produced by request A, you can infer that request B should be executed after request A because you want to consume an existing resource. And the second key technique here is that we have implemented a dynamic feedback loop which learns from past tests so that you avoid the redundant combinations. So for example, if you have a request sequence AB, and after executing request C, you get a 404, you learn that in the future you should avoid this combination, and therefore we can prune a very large search space. So before I move on, these two things are basically the key takeaway I want you to take from this talk, and I summarize as follows. By focusing on the semantic information on the specification of the API, we managed to infer producer-consumer dependencies and be stateful. And by focusing on the semantic information which exists on the status codes of the HTTP protocol, we managed to prune a huge search space and perform meaningful fuzzing. And what bugs are we after here? In the context of this work, we are after 500 internal server errors, which are basically unhandled exceptions. So for the rest of my talk, I'm going to give an overview of how our system works with a concrete example. Then I will present a case study we did on an open source software, and I will talk about some experiences we had with public cloud services, and I will conclude. So in our system, we start with a REST API specification. One typical tool to write a REST API specification is Swagger. We have a compiler in RESTler, which compiles the specification into a Python grammar, basically, which describes how to fuzz its request. It describes producer-consumer dependencies between different request types, and we also generate code automatically to parse the responses and obtain the IDs that are the dynamic IDs that are returned in the responses. With this grammar, we feed it to our main testing engine, and our main testing engine generates and executes tests, which are sequences of requests sent to the target protocol. We generate tests based on two primitives. The first one is we explore combinations of request sequences based on some exploration mechanisms, for example, breadth first and other optimizations. And the second one is we have a dynamic feedback loop, as I said, which basically learns what tests to avoid in the future. And every time we execute a test, we monitor the return codes, and if we find 500s, we basically bucketize them and keep them for further evaluation from the developer on whether this is a bug or not. To be more concrete, here you can see how a Swagger specification looks like when you click it on a web browser. You see a very simple blog post examples, and for example, you see the API, the first API endpoint supports a post request to create a blog post. And you can see here that it expects a body, which would be the content of your article. If you click on a browser, you'll see that most of all the rest look like that. And in the middle now, you see from this Swagger specification, which has also a JSON description, you see that we produce a grammar, which basically starts with the parser of how to parse the response. And then it describes how to fuzz this specific request type. And you can see here, for example, that if we want to fuzz the body of the request, we have primitives like fuzzables. And on the right-hand side, you see a sample test case executed in our network logs. You basically see that we are creating a blog post, and then the response contains the ID of that blog post. So I'm going to continue with an evaluation we did, and basically we asked two questions. The first question is, can the tests that are generated by RESTler exercise deeper server-side coverage over time? And the second question is if RESTler can find bugs in real applications. We will answer these questions in the context of GitLab, which is an open source service for self-hosted Git. It has a pretty large community, it has a fairly big code base, and a very complex REST API. So in our first batch of experiments, we basically ran 5-hour fuzzing sessions on various API families of GitLab APIs, and you can see on the second column the number of request types contained on each API families. On the third column, you see the increase on the sequence length over time until a 5 hours timeout was reached. Fourth column, you see the cumulative code coverage as it increases for longer sequences, and the number of tests we executed. There are a couple of interesting observations here. So the first observation is that as we increase the sequence length, we see that the coverage increases for longer sequences. The second observation is that over the 5 hours timeout that we had, we managed to exercise sequences of requests of length at least 3. And this is interesting basically because we managed to make progress on a huge search space, and I'll give you an example here. If we focus on the commit operations, you see that there are 11 request types, and if we assume that on average each request type has 4 feasible renderings, so for example, you can fuzz 4 different values. You see that we have a search space which consists of 85,000 feasible combinations. And with RESTler, we noticed that for request length 3, we basically executed 250 tests because we utilized the dynamic feedback loop, which told us which tests are redundant, and the dependencies between the request types. So the answer to the first question is positive. Yes, we increased code coverage over time, but our goal here is not to increase coverage, is to find bugs. And although it's a good proxy, we need to move on to our second question and see what numbers, if we found bugs, basically. So in this table here, we summarize the API families of GitLab, and you see 3 columns for the 3 different exploration strategies we have, and I don't have time to describe them. But I want to focus here on total numbers only, and I can talk offline about how they compare and contrast to each other. And I want to first observe that we found 22 new bugs on GitLab on this iteration of experiments, and on top of those 22, we had also found 6 more on a previous iteration of the same experiments. We disclosed all those bugs to the GitLab developers. They were easily reproducible bugs, they were confirmed, and they were fixed. So this result concludes our case study on an open source software, and basically when our tool, so I'm going to give you just a flavor of what type of bugs these were. So here you can see, for example, that when you create a project, then you create a commit message to generate a repository file, a valid commit message, and then you delete the repository file with an empty commit message. And because of conflicting input validation, we basically trigger a 500 internal server error. Most of the bugs that we have out of these 28 are of the same nature. So once our tool matured a little bit, we decided to run similar experiments and find bugs on public cloud services like Microsoft in Azure and Office 365, and basically we ran our tool across 5 services, 3 from Azure, which were resource management services, and 1 from Office 365, which was a real-time messaging service. So the situation here was a little bit different, because once we moved out from a self-contained deployment to public clouds, which we don't control at all, we faced new challenges. And basically, the challenges were related to issues like resource quotas. So for example, on a public cloud, each user has specific resource quotas, and we needed to implement new features. For example, we implemented a garbage collector so that we don't hit that resource quotas quickly, and in order to be able to continue fuzzing. We realized that we had problems with authentication due to short-lived access tokens, and therefore we needed to implement authentication hooks. And we also realized that in complicated services there are exotic naming schemes, and there was a requirement for resource-specific mutations. However, once we had a hackathon to implement all these features, and we unleashed our tools to Azure and Office 365 services, we managed to find bugs in all of those tested so far, which I can't disclose, but they basically look, some of them look similar to the ones I showed for GitLab. So, in conclusion, we built the first stateful REST API fuzzer. We managed to find 28 new bugs on a large open source application. And we found bugs on production Azure and Office 365 services. Now, since this is a new line of work, and we're not exactly sure how important or how dangerous these bugs are. However, our results are preliminary, but they are encouraging in the sense that the bugs we have reported to developers have been perceived seriously and have been fixed. Thank you very much. Here for questions.
Thank you. So I was wondering, so I had a couple of questions. The first thing I was wondering was, are these APIs assumed to be stateless, or the APIs, like there's no assumption in the sense that the APIs can store state on the cloud, so that when you call a second function in your fuzzing sequence, you could be accessing some stored state.
So since they are RESTful APIs, you can have the implicit assumption that there is state.
Okay. So I guess my other question was, so your technique to prune these sequences, I was wondering, and like Patrice is on the paper, I was wondering like if you, there are some like techniques like partial order reduction where you think about commutativity and those sorts of things to cut out the sequences. Like, does that even make sense in this context?
So, are you talking about the technique to prune the search space with error codes, or are you talking about the exploration?
I'm thinking like you prune the search space with some deeper semantic sort of ideas beyond like error codes, right? Like if you know that calling function A and B is equivalent to calling B and A, then you just like don't explore.
I haven't thought about that. Okay. It sounds like a promising direction. However, I don't know if in order to apply something like that, we require access to the source code. It could be the case, and then it changes the game a little bit. The reason why I popped up this backup slide is because so we have different exploration strategies. So the typical breadth first search, or even with this pruning we are doing, it still explores a huge search space, and we have done separate various optimizations to go deeper, hoping to find bugs.
Thank you.
You're welcome.
Okay, thanks for your wonderful talk. I'm from Fuzzing, and my question is, the box may trigger on certain input. So have you applied some techniques to generate the parameters for RESTful API?
So is the question about the dictionary of values we are using to fuzz?
Yeah.
Okay. So basically, we have a feature which we call smoke test. And when you give us an API, we have a small dictionary of values. And what we want to do is we run fuzzing. We want to make sure that at least each request has one successful rendering so that we manage to go further in generations. But I mean, it's customizable and the user can put any value he would like. The only problem here is that if you put more values, you basically explode in the number of combinations. But it's an input, it's a user-defined input. The number of values you want to fuzz and do exotic things and try to crash here and there. But what we have found is that with a small dictionary, you go deeper, and by going deeper, you basically find more interesting bugs than if you put a very broad dictionary with huge strings. Maybe you will crash something very early on, but you'll find shallow input validation bugs. That's the trade-off.
Thank you.
You're welcome.
We have time for one more question.
Thanks for a great talk. I'm thinking about the fact that you're in a distributed systems context and the fact that a lot of these services are deployed on multiple VMs, multiple machines, and of course all of that is hidden usually behind the API. So, question for you is, does Swagger actually specify the kind of architectural constraints? And if not, what sort of assumptions are you making? And is there anything you can do in future work to potentially overcome those?
So, thank you for the question. Good question. There is a new feature introduced in Swagger which defines the time delays between the request sent, but it doesn't specify the way the service is designed, basically. In this version of our tool, we had to consider, however, really what's happening behind the hood, because we implemented the garbage collector, for example, and we needed to consider, okay, so I asked the service to create a resource. I want to delete that resource. How long can I wait? How many times can I delete the same request? The answer is nothing contained in the Swagger can help us. But for things that matter, for example, the garbage collection, we had to implement some heuristics, delays, and things like that. But we can't use the design of the service to capture more interesting bugs like synchronization issues and things like that. Our Oracle is the 500. I'm sorry, they're paging into me. Because of synchronization, as a side effect, we actually managed to cause a bug which looks like a 500, but then when we reported it to the developers, it was something more than that. It was an inconsistency between the cache and the database, and it was a synchronization bug captured by the fact that we had a multi-threaded implementation, and if you have two threads creating the same request ID and deleting it at the same time, you crash the cache.
Okay, let's thank the speaker again.